One.
Hi, welcome back to Math 234.
I'm still your host, Steve Dragoo. Today, we're up against double integrals over general regions. So I mentioned last time that we'd probably just be calling these things double integrals the whole way through, rather than worrying about switching back and forth between double integrals and iterated integrals. So we'll keep that going today. So in particular, the thing that's new about this particular section is that we're no longer going to restrict ourselves to just integrating over rectangular regions. So that's everything that we did last time. But just as long as x and y are bounded strictly by intervals between two numbers, we knew how to do our iterated integral set. Today is about looking at non-rectangular regions, which means one of our bounds is going to be a function of the other variable. So in particular, if I look at this integral on the right, where I'm now going to be integrating over a triangular region, instead of just a rectangle, one of my bounds is the line y equals 5 over 4 x plus 1, which means when I go to calculate that double integral, one of my bounds is going to be that line. Specifically, if I'm doing a y integral first, which is the way I've chosen to do this one, that line is going to be my lower bound. Because when I'm doing my dy integral, I'm going to be going up and down. When I'm looking for my y bounds or my y integration limits, I need to have an upper function and a lower function. If I were doing this as an x integral, which we'll see plenty of examples of in a second, or rather an x first double integral, I'll be looking at a right bound and a left bound. More on that in a second. But right now, we're looking at an upper bound and a lower bound. Those two bounds are going to be y equals 4 as my upper limit, and y equals 5 over 4x plus 1 as the lower limit. But if we just took a moment to think about the sort of answer that we'd expect out of this new integral, where we're integrating over a triangular region, our geometric definitions can still hold true. I am still expecting this double integral to work out to the volume underneath some surface. And if my surface is just the function f equals 3, meaning the plane z equals 3, I can probably figure out that volume. Back when we still had a rectangular region, if I've got an area of 20, because I've got a 5 by 4 rectangle, I'd expect my volume to come out to 60. And if I just cut that area in half so that it's a triangle instead of a rectangle, but still using a height of 5 and a base of 4, just now I've only got half of that base area, I'd expect to get just half of the total volume. So to come out to 30. And I'll find that that's exactly what I get. That works out to 30. Yeah. Either way, I tried to do that integral. So I mentioned in a second, we'd be looking at integrating this thing both ways, both as dy first and as dx first. And that is going to be basically the entire focus of today, is figuring out which order we should integrate in. And if that order is the opposite of what we're given, how do we switch that order? Because we weren't really given one initially. We were just told what our region was going to look like. So we could figure out bounds for either x or y. It was set up nicely to be done for dy first, since I was given my two equations in y equals format. But if I just solve that line, the diagonal line specifically, I guess all three of the boundaries are lines. But if I look at the diagonal line specifically, I can just solve its equation for x instead of for y, right? This guy right there. I wanted to look at it. Which means, hey, don't do that. Which means solving this equation right here for x instead of y, in which case I got 5 over 4, 4 over 5y, 4 over 5y minus 4 fifths. But now that line is the right bound, and my left bound would be the equation x equals 0. So if I'm doing dx first, I want my two limits of integration, or I want my two bounds to be of the form x equals something, and probably a function of y. So that leads into deciding between the two types of integrals that we could do based on the region that we're given. And most of this stuff is more pedantic than it needs to be. So I'm going to touch on it just sort of briefly because it's the way that the textbook introduces this stuff, where we're going to look at where the textbook specifically looks at type 1 regions and type 2 regions as differentiating between whether it's better to integrate dy first or dx first. And really, it all comes down to looking at the region and figuring out which way is going to be nicer. In this first example, I have a clear top and clear bottom function. So if I just want to look from left to right, I have an upper bound and a lower bound without needing to split up my domain. We're going to call that particular region type 1. So that's the first one that we're looking at right here, this guy on that section, because I can completely express the green and the blue lines as y being a function of x, which is kind of important for us. Because now I have functions, I can just do a single integral over that space, as opposed to needing to split up my domain into multiple parts. So if I have a clear top and a clear bottom function, we're probably going to want to do our dy integral first, because there's a top and a bottom. Conversely, if I see a clear right and clear left function, then doing a dx integral first will make more sense, because then I can express x completely as a function of y. Now, those functions could be kind of ugly looking, like these are just some squiggled lines on there. We'll deal with actually working with the functions in a moment. But when we're looking at deciding which order to do our integration in, again, it'll be helpful to figure out, do I have a top and a bottom function, or do I have a right and a left function? And that might change depending on the region. So regardless of which one we do first, by the time we get to our second of the two integrals in our double integral, our limits of integration should be just constant numbers. Just be some real numbered value. So when I'm looking at, in the case that's on screen, my dy integral has bounds of c and d. Those are just going to be numbers. So the second integral should always come back to just integrating between two numbers, assuming I'm doing a definite integral, which is the type that we're looking at right now. Same with the integral above it. When I got to dx, I was just working between a and b for that second integral. I'll always come back to constant bounds. Additionally, by the time I'm finished integrating my first of the two integrals, that first variable should disappear from the equation, because I'll have plugged stuff in for it. So the second integral I get to, in the case of dx, I should only have x's left that I'm integrating. Y won't be part of the equation anymore. And finally, what else should we say? That's still just going over the different types of regions. Putting it all kind of together in a quick, already pre-done out example. If I am going to look at the double integral that's provided right here, so I've got a double integral where y is between 0 and secant x is between 0 and pi over 4, which I'm getting all of that just by looking at the integral itself. dy is the first integral, so I know that those boundaries, those limits of integration are for y. So I want to think of those as the equations y equals secant x and y equals 0. Again, because it's y first. And then the outer limits of integration, the ones on the left integral, tell me what dx should be bounded by. So x equals 0 and x equals pi over 4. Translating that into the region, because I can reconstruct the region just based on the limits of integration, I got this shape where I drew in my two lines, y equals secant x and y equals 0. Maybe I should say my two curves, since secant x is a curve and not a line, but I digress. And then the limits for x were 0 and pi over 4. So I've got x equals 0 being the y-axis drawn in, and x equals pi over 4 being its right limit also drawn in. So that creates my region, and the region is going to be particularly helpful when we need to start reversing our order, which might even be the very first topic we get to in a second. But once we get the bounds set up, for the most part, the integration just occurs the way that we've been doing integration so far. It might fall back on some Calc 1 and Calc 2 methods, but once we get to the integration itself, that part should hopefully be stuff we already know. Granted, it might take some review to get there, but the integration itself isn't the tricky part of this section. It's the finding the correct order, or maybe the best order to integrate in, that tends to be the hardest part of this section. So that's what I plan on focusing on for the rest of the time that we have. So one last quick set here of some things worth talking about. If I have some nasty looking region, like the one here in the example below, where I don't have a clear top and bottom or a clear left and right function, then I can divide my domain up or divide my region up into subregions and integrate it out that way. So looking here on the right, I chose to subdivide, or rather the textbook chose to subdivide the original region D into two different regions that are easier to integrate over, because both of those regions end up having something that I can integrate. And I can subdivide my region the same way that we could subdivide integrals back in Calc 1. If I had some integral that went from A to C, and B was a number in between those two, then I could split up that integral into the sum of two integrals, one from A to B and the second from B to C. We have an analogous idea in our double integrals, except that our domain for the integral is a two-dimensional region instead of just a pair of intervals. But okay, other reasons why we might care about that stuff. One last figure, then I swear I'll actually get to some work over here. If I have this funny looking region here, which actually isn't too complex, it's bounded by some parabola that opens to the right. Looks like it's x equals 1/2 y squared minus 3, and a line, x equals y plus 1. If I try to integrate that as a type 1 region, if I try to do dy first, that means I want a top function and a bottom function. However, my bottom function changes halfway through my domain. Because if I look at the left side of the region, my lower bound is a negative square root function. And if I look on the right side of the region, my lower bound is a line. But the whole way through, the top or the upper limit, the upper bound, was a positive square root function. Something like y equals positive square root x. Probably plus 3 or something in there. Yeah. So rather than wanting to split that region into two separate ones, which I could do, I could do one integral from, what is that, -3 to 0, where I'm bounded on top and bottom by square root functions, and then another integral from 0 out to 5, or now I'm bounded by a square root in a line. It would be easier, I think, instead to reverse the order and look at this thing as a left to right region first. Because then my right bound the whole way through the domain is the line, x equals y plus 1. And the left bound through the whole region is the parabola, x equals 1/2 y squared minus 3. So that's what we'll be doing. Yeehaw. I think I was just in the middle of saying also that we could split up the integral over the two domains. There's our formula for it. If I need to split up the region, I can. And finally, if I just integrate the function 1 dA, I get the area of the region. That'll probably come up from time to time. But that mostly holds from our definition of volume, right? We could always get the volume underneath some curve. And if our curve is just 1, it'll give us the area of the region. But okay, as long as we don't care too much about what our units are. But so let's look at our first example. How long did it take to get to an example? Only 17 minutes. Not the worst time, but I could do better. Anyway, on to this example. So what do we have here? We want to sketch the region of integration based on the thing that we have right there, the limits that we'll talk about momentarily. And I want to write an equivalent double integral with the order of integration reversed. So I currently have dx dy as my integration order, so x first and y second. I want to rewrite that integral so that I can do y first and x second. So let's go look at what that region's going to be. So I'm going to start by drawing a circle. That circle is going to be x squared plus y squared equals 1. So in particular, that's the unit circle. But the reason I chose to do that is because of the two bounds that I'm given for x. I've got this equation, which is going to be x equals the square root of 1 minus y squared. And my lower limit, lower bound, which is x equals the negative square root of 1 minus y squared. Both of those are equations of half circles, split into a right side and a left side because they're of the form x equals something. So solving that equation back to the traditional equation for a circle, I'm going to square both sides, add the y squared over. That's where I got the x squared plus y squared equals 1. And if I highlight those two half circles, they would be these circles right here. Well, that one got a little bit away from me. Right, where I've got a right side and I've got a left side. No, that didn't quite work out the way I wanted it to. And neither did that. All right, one more try, and then we just take it how it is. Cool. Looking at the y limits, it's between 0 and 1. So my region of integration, all told, if I just draw in the line y equals 1, should be the top half of this circle. So that's my region up there. Just the upper half of the circle. It's bounded on the right by the green half circle, on the left by the blue half circle. And then y is stuck between 0 and 1. So I'm just going up from the x-axis to the top of the circle. So that's my region, which, if I want to reverse my order of integration, I want to swap from having a right and a left limit to having a top and a bottom limit, or an upper bound and a lower bound, which means I'm going to need to come up with the equation of the top half of this circle, which I'll highlight there in orange. So that's going to be my upper limit. So if I just take that circle equation and solve it for y instead, I'll get y equals the square root of 1 minus x squared. I don't need to worry about the plus or minus here because the negative square root is the lower half of this circle. Right? The part of the circle that dips below the x-axis would be the negative square root of 1 minus x squared. And I don't need that part of the circle. My lower bound is y equals 0. So, with all that together, we're ready to go switch the order of integration. Let me give myself a little bit more space so I don't run into things. First off, if I'm switching my order, the integrand does not change. So my inside is still 3y. But I'm now going to do dy and then dx. Right, where previously x was my first integral, now y is going to be my first integral. I'm doing y first. Which means, again, I want a lower bound to an upper bound. My lower bound is the equation y equals 0. My upper bound, square root 1 minus x squared. And then don't forget, x should always be stuck between its leftmost number and its rightmost number. When I get to the second integral, it should be only numbers for my limits. So I just need the furthest left that I go, which is -1, out to the furthest right that I go, which is +1. So -1 to +1. Rather than 0 to 1, which was the original leftmost limit, but remember those were y numbers and not x numbers. So again, this is the trickiest part of the new set that we're doing. The integration itself, again, can get a little hairy, but for the most part, it's building on things that we already know. So if you want to see some of that integration, here it all is. I took the liberty of doing it in both directions. So I did it both as written, where I did x first, and then integrated y, and also swapped the order to do it the way that the problem was suggesting. A couple of things worth pointing out in this set. First, I think that the integral is easier doing dy first rather than dx. That's probably why they had us set it up to do it that way. We have to integrate some square root function, needing a u substitution to do it. If we go with dx first, we did it as written. Looking over on the right, I mean, it's not like the worst integral I've ever seen, but it's not as nice as the one on the left. Because after the y integral, I'm just left with 1 minus x squared, which is particularly nice because that integrates nicely. Also, worth pointing out, an integration method that sometimes gets overlooked from, I think this was back in Calc 1, even in odd functions, integrating over similar domains. So if I integrate an even function from -a to a, that's the same as doubling the integral from 0 to a. Or in our particular case, integrating -1 to 1 is the same as 2 times the integral from 0 to 1. as long as I have an even function. An easy way to identify even functions, if it's polynomials, just look for even powers. If every term has an even power, or terms with even powers are going to be even functions. Terms with odd powers will be odd functions. The converse to this statement is that if I have an odd function integrated from negative a to a, that result is just 0. Even and odd both refer to the symmetry of a function. An odd function looks the same on the right and the left. It's a mirror image over the y-axis. Whereas an odd function has rotational symmetry to the origin. So the part that's on the right of the y-axis is equal and opposite the part that's on the left of the x-axis. So it might be worth reviewing even and odd functions because it's a handy method for integration, but not strictly necessary. But anyway, setting up these double integrals. They're super fun. So let's try another example. This time I want to evaluate the double integral. Y from 0 to 1, x from y to 1. And my integrand is sine x over x. Sine of x over x being particularly notable as not an integrable function. You might remember that from back in Calc 1. Or no, Calc 2. I think that's when we started doing that. We're switching the order of, never mind. That's not important right now. So remember, we're doing x first over here. So these two limits should be of the form x equals something, and that something being a function of y. So I've got a star part. What's hopefully roughly a 40-degree angle over here, 45-degree angle over here. And then that. So this is x equals 1. This blue line is x equals y. Conveniently is also y equals x. And I know that y goes from 0 to 1. So maybe, hey, no, don't be like that. I just want, fine, you're just going to break. I didn't want you to work that well anyway. That means that since I'm doing dx first, my region of integration should be right here. Remember that I'm given a right and a left bound. So the green line is my right bound, the blue line is my left bound, since I was doing dx first. Rather than the other side of the triangle. I want this particular side. Where I know some other stuff. Aha! Oh, okay, fine. No. There we go. Good enough. Not good enough. Okay. There we go. One is that bound up there, and also one is that axis right there. So I'm going to need to switch the order of integration in order to solve this thing. So what do I want to do? If I'm going to set that integral up, which I'll set it up right here and then move it over in a second. I want to do y first, which means I need a lower bound and an upper bound for y. The lower bound this time looks like it's just the x-axis, y equals 0. So 0 is my lower limit. My upper limit is the blue line. So y equals x. I still have sine x over x as my integrand, sine x over x, but now I'm going to do dy first. and dx second. And then for my bounds on x, again, they should be just numbers. We're going from 0 to 1. It's looking up here. At this point, it's at 1, 1. And I've also got the origin, 0, 0. Cool. So now let's just do this double integral. So I want to integrate sine x over x dy from 0 to x, which will be sine x over x times the y integral, which will be x minus 0. Right? dy integrates to just y. Since all I have to integrate there is the dy, don't forget, in these double integrals, I can just treat the other variable as a constant, much like partial derivatives. I'm doing the dy integral. X gets treated as a constant. Something integrates to y, plugging in my bounds, I get x minus 0. And I'm still integrating x from 0 to 1. Made that thing a little bit bigger than it should have been. All right, so simplifying this thing, sine x over x times x is simply sine x dx. Where now it's time to actually do that x integral, and the integral of sine is negative cosine. So this will be negative cosine of 1. 1 minus negative cosine of 0, and cosine of 0 is 1. And then I know I said it at the beginning, but I probably should have written it down. Quick note is that the integral of sine x over x is not integrable. Integrable. If memory serves, that came up around the time we were looking at Taylor series in Calc 2. That we have some functions that aren't integrable, and sine x over x is one of them. So that means trying to do a dx integral first on this particular problem just won't come up with any results. So we aren't able to integrate that. At least not with the methods that we currently possess. But some other stuff. Yeah, just a few more examples. Let's sketch a few more regions, do a few more double integrals. So I'm looking at the function that's right here, y over x to the 5th plus 1, and I've got some bounds for x and for y. So I suppose let's start with the region and then worry about how to actually integrate this function after that. So I've got an equation right here, y equals x squared. Y equals x squared. And another one. This will be y equals 0. Right, I'm getting all of that because of the fact that y is in between those two functions. So I'm going to graph both of those. Give myself some coordinate axes. Y equals 0. Or nope. Yeah, sure, y equals 0. I said that first. Let's do it first. It's just the x-axis. Y equals 0. My other graph, y equals x squared, is a parabola. It is a parabola. Close enough. I then know that x is between 0 and 1. So I'll have the line x equals 1 over here, and then also the origin. So 0, 0. Keep in mind that I know x is in between 0 and 1. And then also the point that's up there at 1, 1. Since 1 squared will also be 1. 1, 1. My region then should be that guy right in there. So if I look at this region, just based on its merits alone, either y or x could make sense as the integral to do first. I have a clear top and bottom function with y equals x squared and y equals 0. I also have a clear right and left function with x equals 1 and x equals the square root of y. Just come and write that in because I didn't do it yet. Y equals x squared or x equals the square root of y. So the region itself could be integrated either way. I think that part's fine. Maybe I'd prefer to integrate x squared than square root y, but it might be my integrand that determines which order I should do first. Is if I try to look at this thing, if I attempt to do x first, I have to integrate what is effectively 1 over x to the 5th plus 1. And that doesn't look great. I could try a u substitution, but then du is 5x to the 4th, which I don't have that present in my integrand right now. So u substitution isn't going to work for that thing, which means instead I'd have to do integration by parts. And I could see that integral spiraling out of control rather quickly because I'll have to keep taking derivatives of x to the negative 5, which are just going to continue to get worse. So moral of the story there, I don't think dx is a good first step because I don't have a very nice integral for x. So I am going to worry about that later and try dy first because that integral looks a lot nicer. Which will end up being a common theme with a lot of the multiple integrals that we're doing, that we kind of look at our integrand and just decide to integrate whichever function's easiest first. So with this mess, again, changing the order of integration will not impact the integrand itself. That part always stays the same, unless I'm changing my variables, which we're not to that part yet. So the integrand is still y over x to the 5th plus 1. The only thing I really have control over is whether I'm doing y or x first. And I landed on y first, which has upper and lower limits of x squared and 0 respectively, meaning that x is between 0 and 1. Because then this thing integrates to, if I just integrate y, what am I going to get? So I'm integrating y dy, which would be y squared over 2. So I'll have a 1/2 that shows up. I'll also have a something squared. That's what I get when I'm plugging in y. The thing that I'm plugging in is x squared and 0 for the upper and lower limits. So x squared squared minus 0 squared. So that'll just work itself out to x squared squared times I still have 1 over x to the fifth plus 1 dx from -1 to 1. So clean that up just a little bit. Wait, -1 to 1. That doesn't sound right. 0 to 1. This looks like 1 over 2 times the integral from 0 to 1 of x to the fourth power over x to the fifth plus 1 dx. And now I actually have a nice looking u substitution. Something like u is x to the fifth plus 1, meaning du is 5x to the fourth dx. So this thing integrates to 1 over 2 times 1/5, since I'm missing the 5 on that x to the fourth. I'll have the integral of du over u, which comes out to natural log of u. So 1 to the fifth power plus 1, plus 1, minus the natural log of 0 plus 1, plus 1. And then that cleans up just a little bit. 1/10 natural log 2 minus 1. Zoom that back out for a second. Again, after the first step of figuring out what our order should be and hopefully landing on a good order, everything else in the problem just falls back on Calc 1 and Calc 2 integration methods, depending on what we get into. So the new stuff really is all about setting these things up correctly, and that's where most of the challenge lies. I'm not saying the integration is easy. I'm just saying we've learned it before. So it's the new setting up the integrals that I think is the most complicated part. But hey, what do I know? Cool. Keep practicing with changing our order of integration. So this time we're not even given a function we can integrate. We're just told we've got f. And we have our two limits, which we should keep coming back to. This thing is dy first, which means we're back to y equals a function of x for my two bounds. Oop, I said y equals a function of x. So y equals natural log x and y equals 0. So I can come through and graph those two things. Y equals natural log x is a curve, something like that. Y equals 0 is still our x-axis. I also have bounds for x. So bounds for x. They're at 1 and at 3. So I'll have a vertical line at x equals 3. And then also a vertical line at x equals 1. So my region must be this one. Where again, I have the curve y equals natural log of x, or x equals e to the y. I could write that green line as either function. And if I want to reverse this order, that means I want to do dx first. So f of x, again, does not change. It's just dx, dy. I've got to do x first. So my new bounds should be right and left rather than top and bottom. I'm doing dx first. So my right bound is x equals 3. If I look to the right side of the region, that right side limit is x equals 3. And if I look to the left side of the region, it's the green curve, which written as a function of y is e to the y. E to the y. And then for the y bounds, I'm going to need the interval over which y is defined, right? Basically, project this shape onto the y-axis and find that interval, which means I'm looking at my lower point, which is at 1, 0. And I'm looking at my upper point, or I guess my minimum point, my maximum point from the y perspective. This is at 3 natural log 3. So my y limits are 0 to ln 3. And they should be y values. And I just need to find my lower y value and my upper y value. Minimum y and my maximum y. All right, and then just one more. Evaluating this function. Again, looking at my integrand, I've got e to the x to the fourth. And no amount of u substitution is going to let me integrate that thing right away. So it's telling me to do dx first, and that looks like a bad time. So, since I can't do the integral as written, I'll swap the order. I've got x equals 2, and I've got x equals y to the 1/3. So if I go create a graph of that region, my couple of curves ought to be x equals 2 and x equals, let's try that one more time, x equals y to the 1/3 or y equals x cubed. And I was doing dx first. So my region should be right in here. If I'm looking right to left. And my y bounds just tell me I'm at 0, 0, and I'm at 2, 8. 0 to 8 for y. So if I reverse that order, I want to do dy first, e to the x to the 4, dy, and then dx. Y looks like it's bounded below by the x-axis, which is y equals 0, and above by the blue line, x cubed. X then just being bounded by 0 and by 2. And then this thing is rather nicely integrable. I'll have a y integral from 0 to x cubed. So this is just x cubed e to the x to the 4 dx from 0 to 2. Again, a rather nice u substitution gives me 1 over 4 e to the x to the 4th. So 1 over 4 e to the 16 minus e to the 0, which is just 1. Again, adding in a little bit of detail here. If u is x to the 4th, du is 4x cubed dx. And that's it. I'm only slightly over on time. Thought it was going to be worse when I start of this problem. Very cool. So that's double integrals. So one quick note. If you're looking at the order of the notes and the order of the pre-class videos, it has section 10 next, which is change of variables. And we're not going to do that. So we're just going to continue on in textbook order. Monday is section 4. Change of variables was moved back to its original position at the end of chapter 15 because it definitely belongs there. So Monday is double integrals in polar coordinates. So look forward to that. All right, I'll see you then. Okay, bye, 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 bye.